then probably the most important concept was this notion of what is called a resultant. So, sorry, 1 second. I don't know why we are not live yet. Okay, apparently only now we went live. I don't know. Okay, so the second concept that we saw was the notion of resultance. And resultance is a way of trying to capture whether or not two polynomials share a non-trivial common factor as some condition based on its coefficients. So formally speaking, a resultant is some algebraic expression involving the coefficients of f and g. So in particular, it's basically the determinant of this matrix, where every entry in this matrix is one of the coefficients involved. Okay, and somehow it has this miraculous property that this particular expression is equal to 0 if and only if f and g share a non-trivial common factor. The notion of non-trivial is a little important in the sense that if you're looking at a resultant with respect to x, then your non-triviality is also with respect to x. By that, what we mean is we are asking, does f and g share a factor that has non-trivial degree in x? That is, the degree in x is at least 1. Okay, so like for instance, if f and g share a factor that is completely only in terms of the y's, that is, it's not even dependent on x, it may not show up in the resultant being non-zero, because in the world where you're only dealing with univariates in x, anything in y you're thinking of as a scalar. That's the reason why there might be some confusion with respect to this. But normally speaking, what we will be working with, we will be dealing with polynomials where f and g are both monic in x. So there are no factors that depend only on y. Okay, so therefore that problem just goes away. It is just convenient to deal with monic polynomials in x. Okay, so this is what the resultant was. And so this was this remarkable sort of observation about the resultant, which is what makes it super useful. And in particular, it gives you a way of mentioning precisely when you start coming up with these spurious factors. Like one concrete example which ended up being used in the GCD algorithm was that suppose you have two bivariate polynomials u and b, which actually didn't have any GCD. Like the GCD was trivial. But suppose I substitute y equal to a, and suddenly the GCD now becomes non-trivial. Okay, and the resultant sort of tells you that why such a thing is happening. And it says the only reason something that didn't have a GCD will suddenly now end up having a GCD after you substitute y equal to a is because the resultant originally was a non-zero polynomial, but when I substituted y equal to a, it became 0. So it's telling you it is degenerate. This particular choice of a was degenerate because you ended up killing the resultant. So as long as you choose a point a such that the resultant is non-zero, then somehow you don't end up getting any spurious factors. So that's the whole point of the resultant, to sort of give you a way of capturing when you can avoid, when you can somehow argue that there are no spurious factors. So from that perspective, it is important to note that this is a polynomial purely in the y variables. I mean, I'm assuming that both f and y are bivariates. So all the entries involved here are basically polynomials in y. So when you compute the determinant, you'll get something in y. Okay, and it's also useful to note that the degree of this polynomial is at most something like 2d squared, where d is like an upper bound on the degree of f and g. Because this is like something that looks like a 2d cross 2d matrix, and every entry has degree at most d. So a stupid bound is just 2d squared. Okay, because things like this will be useful because you can somehow say that how many different a's can make the resultant equal to 0. Well, it's a 2d squared degree polynomial. So at most there can be at most 2d squared many a's, etc. So it lets you capture it in that sense. And we just use this to come up with an algorithm to compute bivariate GCD in polynomial time. Okay, we just sort of piggybacked on the univariate GCD by doing these projections and computing it. It's okay if you don't, if you didn't completely follow the bivariate GCD algorithm, just take that for granted. And we won't really need the innards of that particular algorithm in today's class at all.
The rest of the element in the matrices are 0, right?
Oh yeah. Whatever I have not written, all of these entries, they're all 0.
And and if one thing, so I was not there for last half an hour, I guess. So the degree might be different, right, for f and g, right?
Yeah, it could be different. I'm just saying that d is some upper bound on the degree of f and degree of g.
So it might happen that the last row might be all 0 except the corner.
No. So okay, so the resultant in particular, there you need to say that this guy has degree. I'm assuming that it has D1 in X, and this guy has degree D2 in X. So the resultant is actually a D1 plus D2 cross D1 plus D2 matrix. So here I'm going to be precise, but when we are coming up with degree bounds, if all I want to know is like how large can the degrees be, in that perspective, I'm just going to say that, okay, D1 is at most D, D2 is at most D, so the degree is at most like 2D squared. But the resultant, the definition of the resultant, of course, you need to be careful about what the degrees are. Otherwise, like you pointed out, it could be the case that this row is just 0.
No, that rows might not be 0 if the D2 is higher than D1. But if the D1 is higher than D2, then
I mean, if D1 is higher than D2 and FD1 is equal to 0, then it would sort of become that this row becomes 0 or something, right?
Yes.
So so that's why we don't want issues of that sort. So just make sure that the matrix that you're writing down is of the right size. It's of the correct size.
Okay. So one more thing. So the resultant you want in means that it can the polynomial in fxy you can visualize in both way, in x or in y, right?
Good. So that's right. So the resultant will tell you whether or not. So the resultant with respect to x being 0 is saying whether they have a GCD which is non-trivial from x's perspective. So if you take the resultant with respect to y, then that will be 0 if and only if there is a non-trivial GCD with respect to y's perspective.
Okay.
Did that make sense? I mean,
yeah, that I understand. I was trying to think that is there any easier way to suppose the degree of the determinant with respect to resultant y is more than the degree of the if you consider the resultant with respect to x. Okay. So in that case, if we can we say something by not calculating explicitly y or x separately, but calculating one, and if we found there is a non-common factor, then we can something tell about others.
I mean, I'm thinking of a possibility that, maybe f and g share a common factor which is purely a function of, let's say, y alone. So then when you take the resultant with respect to x, I mean, you might get something which is non-zero, because resultant with respect to x will only tell you whether or not there is a common factor that is dependent on x. But on the other hand, you will notice that resultant with respect to y is actually 0, because there is a common factor that is non-trivial with respect to y. But I don't know if like your question is like, if I look at the resultant with respect to x and resultant with respect to y, and somehow by looking at these two things, can I say something different? I don't know off the top of my head. Yeah.
Okay, sir.
Okay, good. So let's proceed. So here is one really nice exercise. I'll write it as an observation, but I'll give you a hint, which is it has this. There's also another property that whenever you're looking at the resultant with respect to with respect to x of two polynomials f and g, you can always write this as something times f plus something times g, where a and b are both polynomials in x and y. Okay. And it's an unusual thing because notice that the left-hand side is something that depends only on y. Whereas the right-hand side is some expression that looks like something that involves both x and y. So in some sense, the resultant is a way of eliminating the variable x by taking some combinations of x and y. So this also resultant is also something that shows up a lot in this sort of a subfield called elimination theory. So resultant is one concrete way of doing that. And the proof of this is actually very simple, which is you just take this matrix and do some suitable row operations so that the top row basically becomes, every entry becomes a multiple of f or a multiple of g. Okay, then when you expand out the determinant across row 1, well, you will basically get f times something plus g times something. Okay, so I'll let you think about it. In fact, it probably already suggests exactly what row operation you should take, because you basically have all the coefficients of f in front of you. If you wanted to build f, what would you do? So yeah, so just think about it and that will tell you. So this is the recap that I want you to take away. It's okay if this is something that you didn't entirely follow. Just take for granted at this point that these whatever the resultants can be used to compute bivariate GCD in polynomial time. All right. So with all this out of the way, I'm now going to completely describe to you, okay, not in its entirely. So describe to you the bivariate factorization algorithm, but I'll tell you partially because then I want to maybe try out some whatever, I mean, some sage code to sort of demystify like a trick that is used in this algorithm. Okay, so here is this, by the way, what I'm presenting, the bivariate factorization algorithm is due to Gathen and Kaltofen from the 80s. I don't exactly remember when in the 80s, but it's sometime in the 80s. And we're going to, I mean, I'm going to sort of just say that, we'll work with a certain simplistic case. Depending on how much time we have at the end of the lecture, I will justify why this is without loss of generality. Okay, so the first thing is I'm going to assume that f is monic with respect to x. Okay, by that what I mean is if I look at the highest degree term in terms of x, its coefficient is just 1. That the highest degree term doesn't look like x power 7 y power 4 or something. So the highest degree term is completely, it's just 1. So that is one I'm going to assume. And secondly, I'm going to assume that f is square free. And this is usually where the GCD comes up because you will take a GCD with respect to its derivative. I mean, one of the two derivatives with respect to x and with respect to y, and somehow eliminate these repeated factors in some sense. Okay, so that is something that we can assume with the loss of generality using the standard tricks. I'm going to make an extra leap of faith and sort of say it's not only that f of x comma y is 0. I also want f of x comma y is square free. I also want f of x comma 0 to be square free. That is, this polynomial ends up being square free even under the substitution y equal to 0. Okay. So firstly, it's unclear why I need this, but we'll get to that shortly. And secondly, it's also unclear why can I assume this without loss of generality. And that is something that we will get to towards the end of today's lecture. Okay, I mean, now you should already, when you should already be thinking in terms of, oh, this is like saying that if I look at the resultant of f and its derivative, that resultant should not vanish when y is set to 0. That's what it means to say if something was square free to begin with, I don't want it to suddenly become, somehow involve squares when I set y equal to 0. But anyway, don't worry about it. We'll just say that, this is the set of polynomials we are dealing with. That's the polynomial that's given to us, and we are asked to come up with some factor for f. That's the goal. Either do that or figure it, or basically output that f is irreducible. Okay. So how do we proceed from here? I mean, like, how do I even start this entire process? So the amazing idea of Gathen and Kaltofen was, let's do the one thing we know how to do and try to slowly improve on top of this. Okay, and the idea was, let's look at the polynomial f of x comma 0. Okay, now this is a univariate polynomial because all y's are gone. Y's have been set to 0. Okay, and let's factorize that first. Okay, and then let's somehow try and build on top of that factorization and somehow try and figure out the factorization for f of x comma y overall. Okay, so let's say suppose I factorize it and I end up getting some g0 of x and h0 of x. Again, this is something that we know how to factorize because, we know how to do univariate factorization. Okay, and so this setting y equal to 0 is the same thing as basically going mod y. Right, so I'm going to basically pretend as if g0 and h0 are bivariate polynomials when they really are not bivariate polynomials. They're univariate polynomials in x. Okay, so the above equation is the same thing as saying f of x comma y can be factorized into g0 of x comma y and h0 of x comma y mod y. By that, what I mean is, if I take the difference of f with g0 times h0, every monomial is divisible by y. Ideally, I want to get a proper factorization. I want f minus g0 h0 to be equal to 0. At this moment, I don't have that. All I know is that whatever terms I get, they're all divisible by y. Okay. And what we are going to try and do is we're going to try and improve this factorization. So right now, this is a factorization mod y, which sort of says that the error terms are all divisible by y. And what we want to now do is similar to what we had done earlier, which is like, okay, can I somehow now ensure that the error terms are all divisible by y squared, and then y power 4, and then y power 8, etc., etc., etc. So we'll want to do this sort of lifting process or the Newton iteration sort of process.
Why you required one of the variable is monic?
So I guess it will become clear at a later point. At this, so far it seems like it's not relevant, but it will hopefully soon become relevant as to why. Because there'll be points in the middle where I'll be using resultants and stuff like that.
So,
and for all of those situations, monic is good.
So basically, when you were, I'm guessing that you will use for something for x comma 0, right? Where you will use the monicness.
Sorry?
For x comma 0, you will use the monicness.
Like, for example, I know for a fact that this has not suddenly become 0 now, because the leading term was something that was independent of y, and that continues to stay alive.
Yes.
So it's just that it will help us deal with a bunch of these corner cases. But monicness will also play a crucial role very shortly. So there is a reason why monicness will come up.
So you are firstly you are assuming that fx comma 0 can be factorized into g0 and h0, right?
Good.
Then you are
so
trying
if f of x comma 0 is irreducible, notice that already implies that f is irreducible. Because if f split into two factors, then I can take those two factors and then set y equal to 0. Then I should have gotten two factors, right?
Yes.
So at this point itself, if this was impossible, if there was no way to write f as g0 times h0, I already know f is irreducible. So I will, in that case, I will just return f is irreducible. Suppose I find a factorization. I find some non-trivial factorization. So I have some g0 and h0. And at this point, I know that both g0 and h0 are both monic in X as well. Because we start off with a monic in univariate polynomial, you factorize it, you will get some monic univariate polynomials. Okay, but this monicness will be useful because now I'm going to try and improve it, and in this improvement step, monicness will play a crucial role.
So you are trying to prove the converse part, right? If the univariate can be factorized, then we will try to see that we can factorize the bivariate one.
So the converse will not, I mean, just at the face of it, the converse is not true. I mean, it's not the case that f is factorizable if and only if this is factorizable. That is false.
Yeah,
but we are hoping to somehow from G0 slowly figure out either a proper factor of f or somehow figure out that f is actually irreducible.
Oh, that can be that it's a theory that it can be either for some general class classification we can get it.
Yeah. So we'll see. I'll show you some examples also exactly what happens. So at this point, what I want to do is I want to improve the current factorization. Okay, and we will do something that we have been doing all throughout. Okay, which is you write g1 as g0 plus, I don't know, some alpha times y. I mean, you perturb, like we had done in our previous lifting case. And similarly, we'll write h1 is equal to h0 plus beta times y. Okay, we are trying to figure out what alpha and beta should be. I don't know at this moment, but we'll let the equation somehow tell us what they should be. Okay, and what do I know to begin with? I know that f minus g0 h0 was something that was divisible by y, because every term was divisible by y. Okay, so let's just write this as gamma times y. So this is our current situation. I have g0 and h0. I'm supposed to figure out what g1 and h1 should be. And in order to figure that out, I need to figure out what alpha and beta should be. Okay, so let's just write down what is f minus g1 h1. This is going to be f minus g0 h0. What should this be? So this should be this minus of, okay, let me just write this. G0 plus alpha y, h0 plus beta y, okay, which becomes f minus g0 h0 minus of alpha h0 plus beta g0 times y plus alpha beta y squared. Or maybe there's a minus alpha beta y squared.
Alpha beta is the scalars.
I mean, at this point, I don't know. Alpha maybe is a polynomial. polynomial. Who knows? I mean, right now we are letting alpha to be floating, and we'll figure out exactly what alpha and beta ought to be. Okay. And I want to look at this equation mod y squared, because I'm hoping that f is equal to g1 h1 mod y squared, because that's our improved step. And for that to happen, so this is the same thing as, so f minus g0 h0 was gamma times y. So this is basically y into gamma minus alpha h0 plus beta g0, the whole thing times y. And mod y squared, I can just ignore that last term because that was anyway already divisible by y squared. So if I want this to be equal to 0, oh, sorry, I put 2y. Okay, so if I want this to be equal to 0, then I somehow want to choose alpha and beta such that gamma equals alpha h0 plus beta g0. Okay, so far we haven't used anything about g0 and h0, but
Why you
suppose it
need
were
zero?
Sorry?
It might be some polynomial in y also, right?
It could be. I'm just trying to somehow make sure that it is equal to 0 for a stupid
Okay,
reason. Just play
okay.
along with it. So,
Okay.
so what is one way in which I can assume this? Suppose it were the case that g0 and h0 were co-prime.
Yes.
Okay, then there exists some a and b such that a g0 plus b h0
equals to
this
gamma.
is equal to 1. Okay, once you have that, you can now set alpha to be equal to gamma times b and beta to be equal to gamma times a, and this will basically become gamma times a h0, I mean a g0 plus b h0. That cancels this gamma and all is done. Okay, so I need to somehow make sure that the factorization I started off with has the property that g0 and h0 are co-prime. Now, if f of x comma 0 looked like g0 power something, there was no way for me to have done this. But on the other hand, if I know for a fact that f of x comma 0 is square free, then I know for a fact that any factorization I find, if once I split it, g0 and h0 are going to be like co-prime. And that's the reason why we needed this second step. Okay. So that was so at least this hopefully tells you what we are doing at this point. Okay, so therefore at this point what we have that f is equal to g1 h1 mod y squared. Okay, and now I want to ask the following. Suppose I now want to go from, I want to get f is equal to g2 h2 mod y squared, mod y power 4. I want to basically run this entire process again. Okay, so but it's not, I mean, I need to make sure that the invariant, whatever properties I had about g0 and h0 earlier, I have those properties about g1 and h1 at this point. One of the properties about g0 and h0 was that there exists a and b such that a g0 plus b h0 was equal to 1. So let's write it as mod y. I mean, since it's equal to 1, even without the mod, it's of course equal to 1 mod y. Suppose I can somehow ensure that there exists a1 and b1 such that a1 g1 plus b1 h1 equals 1 mod y squared. They're sort of co-prime in that sense. If you somehow manage, right now we have found some g1 and h1. We don't even know if this fact is true at all. But suppose it were true, then notice that you can run exactly the same algorithm, whatever we did right now. I mean, you'll just, I mean, wherever there was a y, you will replace it by y squared or something like this, and everything else will just follow. Okay, so so in order to apply this, so we need to or rather what I want to say is that if it is the case that our g1 and h1 also satisfy that a1 g1 plus b1 h1 is equal to whatever 1 mod y squared, then we can repeat this process. Okay, so, and this particular operation of repeatedly coming up with better and better things is what is known as Hensel lifting. Okay, so I'm going to write down the entire Hensel lifting lemma. It's a long lemma, but it has many subparts in it. Each of it are like very clean to explain. Okay, so I'll go over it slowly. Okay, so Hensel lifting lemma basically says the following. Suppose you have a bunch of things of the form f, g, h, a, and b, and a parameter I. This is your input data. Okay, like this is the, I mean, we were starting with g naught, h naught, some a and b, and I being equal to 1 in the sense that we were having some equation mod y power 1. Okay, so what was the data satisfying? The data satisfied two properties. F equals gh mod y power I. That was property 1. Property 2 was ag plus bh equals 1 mod y power I. Okay, Hensel lifting is a way of saying that then we can actually compute a lift of this data to get some data, some new thing, g prime, h prime, a prime, and b prime, that satisfies everything that you started off with. That is now f equals g prime h prime mod y power 2i. That is the accuracy has somehow improved. Instead of mod y power I, you now have mod y power 2i. And furthermore, the a prime and b prime are such that a prime g prime plus b prime h prime equals 1 mod y power 2i. Furthermore, this g prime is really a refinement of g, and an h prime is a refinement of h. That is, if you look at them mod y power I, they look the same. So basically, g prime and h prime were constructed by only adding terms that were divisible by y power I. Sorry, the first part of Hensel lifting is just existence. And not just existence, it's the existence in an effective way. In the sense that we'll exactly tell you what these g prime, h prime, a prime, and b prime are. Given this data, there is an algorithm to compute g prime, h prime, a prime, and b prime. That's part 1. Okay. The second part about it is that this lift is actually unique in some sense. That is, suppose we'll call anything that satisfies star a valid lift of the input data. So let's say I compute one possible valid lift, which is g prime, h prime, a prime, b prime. And maybe somebody else computed a different lift, which is g prime, g double prime, h double prime, a double prime, g double prime. Then there is a sense in which we are both computing the same thing. In the sense that it basically says your g prime and my g prime are related by some factor of 1 plus u. And h prime and h double prime is related by a factor of 1 minus u, where u happens to be 0 mod y power. So g prime h, or rather g double prime h double prime is equal to g prime h prime into 1 plus u into 1 minus u, which is like 1 minus u squared, and u squared is divisible by y power 2y. Okay, so there's some notion of uniqueness. That is, if you're willing to tolerate multiplications by terms of the form 1 plus u or 1 minus u, any lift that people compute, they're actually the same. Okay. Yeah, go ahead.
So here, so right now so this is what we have just a univariate factor. Like given that it's square free and all of that is true, then we get a univariate factorization, and then we are trying to improve the y part of the bivariate factorization. One part. But why do we need uniqueness here?
So we don't, but it'll end up being useful in the proof, because it's actually unclear. If I just lift something, am I actually going to figure out the factor or not?
I mean, you are always
every
getting
time
a
I
correct
lift it, yeah, but it's a factorization mod y power something, right?
And when once you reach some y power, like a large enough y power, then you must.
Excellent. Okay, keep this point in your mind, because we are going to try out some examples, and then we will see exactly what happens there. Yeah, I mean, it does feel like, I mean, yeah, of course, you just lift it enough and it should be fine, right? I mean,
yeah.
So we'll see exactly what goes wrong. Okay, but yeah, but there's a lot of truth in what you're saying. That's going to be the goal. We're going to start with the univariate factorization, lift it high enough, and somehow hope to recover a factorization of f from this. That's the goal. That's what we are going to try and do. Okay. And now coming back to Saurav's question, which is why did we care about uniqueness? And the uniqueness is important because suppose you know that F is unique and G is unique. Sorry, F is monic and G is monic. And then I ask you to lift it to some G prime, which I also want to be monic. Then, in fact, this uniqueness is truly unique. This 1 plus u, 1 minus u factor just goes away. In fact, there is a unique G prime, like mod y power 2i, such that there is only one possible lift if you restrict yourself to monic lifts. That's the point. So the previous uniqueness is like uniqueness up to a factor of 1 plus u. The moment you throw in the fact that I'm additionally putting the constraint that G and G prime are both monic, then basically there is only one lift. You don't even have more than one choice.
I have a small question with something different. So if we not assume that our polynomial it's not monic, but if we try to factorize it in our open bracket x, I mean the quotient space also, the rational polynomials, and then try to get it, means if it is not monic, then we can observe it in Rx rational functions, where I can get a function so that it can make to monic, and I do the
one second. So you're saying that I want to think of f of x as something in, let's say, fy, where I mean in the sense that it's univariate in x whose coefficients are these rational polynomials.
Yes. Okay. And I can make it monic there. Then I do the and then I use this lemma and try to somehow get it back. Is it
so firstly, this lemma works only when you're going modulo y power something. So secondly, we don't know how to factorize here. We only know how to factorize when this was an FP. I mean, or in general, a finite.
I'm saying that if our it is not monic, okay, then I can treat the fx element in f round bracket y in close bracket x, right? And I divide it and make it monic in x.
Yeah, then so it's just that you will have these fractions which get a little annoying. But actually keep that thought, because towards the end of the lecture, we will see how to handle non-monic f. And the trick is very similar to what you're suggesting. Okay. In fact, you don't need to, you can actually work in the original world itself by instead of factorizing the original polynomial, factorize a different polynomial. But we'll get to that. But for now, let's just assume that f is monic, because it helps, a lot of other details become much simpler. Because if f is monic, I can now insist that the G I start off with is monic. And I can insist that throughout the lifting process, I only deal with monic lifts. And uniqueness, this monic uniqueness will basically tell me that the lift that I have is unique. Even if somebody else did a different lift, they will end up with the same answer. Okay. So the proof of this is sort of uninsightful. I will just basically tell you precisely what this G prime, H prime, A prime, B prime are, and you just need to verify. We just did a short example. The short example, you just need to expand on top of that. Okay, so G prime, basically, we already saw what G prime and H prime was. It was basically G prime plus B gamma, H prime plus A gamma, where gamma happens to be this F minus GH. Right, so that's what we did. And what are the A prime and B prime going to be? It's basically the old A into 1 minus delta and B into 1 minus delta, where delta is basically AG prime plus BH prime minus 1. Okay, so, and you just plug this in and just convince yourself that this actually satisfies star. It's a calculation and it's not particularly insightful. And showing uniqueness is also not that difficult. I mean, the U that works is something that I have written here. That is, if somebody gave you a different lift, let alpha be their difference and beta be the difference between H's. And if you set U to be equal to this particular term, turns out that G prime and G double prime are related by this U, and H prime and H double prime are also related by this. Okay. The monic uniqueness thing, I will leave it as an exercise, maybe with just an example to sort of convince yourself as to if you are forced to make it unique, forced to make it monic, what is the only u that you can use? So that is, suppose let's say G was originally this, which looked like x power 4 plus a bunch of lower order terms. So it's monic because the highest degree term looks like x power 4. Okay. But I lifted it and now I end up with some stupid G prime that suddenly has higher degree terms in terms of x, but they all come accompanied with some large power of y. So if this was the situation, what do you need to multiply to G prime so that now it becomes a monic polynomial? I want to cancel off this entire thing. Okay, so just think about it. There is a particular choice of u that will show up for you, and somehow that actually happens to be unique. Okay, so I leave this as a, the proof of the Hensel lifting lemma. It's not particularly insightful beyond what I did in the as a base case, just to go from mod y to mod y squared. The rest of it is just calculations. Okay, so far so good. So the Hensel lifting is clear, and notice that this is completely algorithmic. I give you G, H, A, and B. You know precisely what is G prime, H prime, A prime, B prime, because I'm telling you exactly what they are. Okay, so there's a very simple algorithm to just compute the lift that you want. And because the Hensel lifting is set up such that your original invariant ends up getting maintained, thus justifying the name invariant, it basically means that you can apply this again and again and again. So you can start off with something that was just a factorization mod y. Now you get mod y squared, mod y power 4, mod y power 8, and you can go as high as you would want to. Okay, so now let me just describe what is the algorithm. Okay, this is basically what Varun had suggested, and I'm saying it's a nice case because this is the assumption that I have on F. It happens to be monic, it happens to be square free, and it continues to be square free when y is set to 0. Okay, so here's the algorithm. We'll try to factorize f of x comma 0. If this itself is irreducible, then just say that f is irreducible. Okay, otherwise it factors into some g0 and h0. Okay, let's just say that g0 is one of the irreducible factors of f, and x0 is whatever else was there. And of course, g0 and h0 are currently monic. Okay, and we can always find the Euclidean GCD algorithm to figure out some suitable a0 and b0 such that a0 g0 plus b0 h0 is equal to 1. Okay, so we now have the necessary invariant to apply Hensel lifting. Okay, because I know I am given a g0, h0, a0, and b0 that satisfy the two properties, which is that f of x comma y minus g0 h0 is 0 mod y, and a0 g0 plus b0 h0 is 1 mod y. So I can apply Hensel lifting, and you can apply this repeatedly. Let's say you do this some k times. So after k times, you will end up with some two polynomials, I don't know, gk and hk. Okay, that form a factorization of f mod y power 2 power k for your choice of k, and we'll just assume that this k is somehow large enough. Okay, maybe one of the things that Varun suggested was that just choose k so that this 2 power k starts exceeding d or something, because f is a polynomial of degree d only. So if you get a factorization mod y power, I don't know, something like d squared or a d cube or something, it must have some information about the actual factorization, feels like. Okay, and once you lift it, we want to do something. So it's unclear what we want to do. So Varun's suggestion was, shouldn't gk already be a factor? Okay, so that was one thing that we need to verify. So let's just try out some examples on Sage, because otherwise I think it's sort of hard to really convince yourself as to what is happening here. Okay, so I'm going to I'm going to try and show you some Sage code to see. So is my the browser, the Sage thing visible?
Yeah.
Okay. So good. So I'm just building a polynomial ring and two variables, and this is the Hensel lifting the algorithm. And I also had this iterated Hensel lift so that I can do this multiple times. Now, if I want to do this k times or something, I just feed in a suitable parameter k. Okay, so let's take up a couple of examples. So the first example I'm choosing is some bivariate which factorizes as x plus y plus 2 and x minus 3y plus 1. Okay, so this is what it is. So what is the first step of our algorithm? We basically look at f mod, so let's look at f mod y, and that is x squared plus 3x plus 2. And if I factorize that, that factorizes as x plus 1 and x plus 2. Okay, so far so good. So now what we'll do is we'll take g to be equal to x plus 1, h to be equal to x plus 2. So that is our initial factorization. This is basically g naught and h naught. Okay, and now we'll find the whatever the a and b such that a times g plus b times h is equal to 1. Okay, and this is what I need to feed to the iterated Hensel lifting. I need to start off by saying, here is a factorization of f in terms of g and h with the Bezout coefficients being a and b, but this is a factorization mod y, and I want you to lift it, let's say 5 times for k equal to 5, so that we eventually end up with, I don't know, y power 32 or something. Okay, and I am going to insist that I want monic lifts. I give you a monic lift, I want a monic lift.
And what was our fxy again? Like what is
so fxy was this thing, x squared plus it's some degree 2 polynomial.
Right.
Okay, so certainly feels like y power 32 is like way higher than we should need, right? So let's lift it and let's actually print what gk and hk are. And look, I mean, you just lifted and you just recovered the factors that you were supposed to, x plus y plus 2 and x minus 3y plus 1. Okay, great. So we did find our factors. So here is an example where the intent, our mental picture of what this algorithm is supposed to do is working fine. Okay, now let's try out a different example, which is x cubed plus x minus y, which actually happens to be irreducible. So I want to know, had we run this entire process, what would have happened? Okay, so what is f naught? I mean, like mod y. I mean, f naught mod y is maybe I should have written it into 2 things. I'm going to put this here. So if I factor f naught, I actually get x into x squared plus 1. I mean, which is again not surprising, because like if I go mod y, I basically end up with x cubed plus x, which we know factorizes as x into x squared plus 1. So let's take g to be equal to x and h to be equal to x squared plus 1. And let's once again compute the whatever extended Euclid thing. You get some Bezout coefficients a and b. And now once again, let's lift it. So by the way, I hope my Zoom window is not coming in the way. Is it coming in the way?
No.
Okay, good. So now let's try and lift. So we computed this. Let's lift gk and hk. And let's try and get a sense of what does gk look like. And you see it's some garbage. I mean, like, you know, we ended up lifting. So, I mean, Hensel lifting tells us that you started off with something. So every time a lift exists, so you will keep getting lifts, but obviously you look at this polynomial and it's like, okay, this is obviously not a factor of f. So maybe it is suggesting that, okay, maybe this is how we figure out that f of x comma y is irreducible, because the lift doesn't seem to be helpful. Because there's all sorts of random sort of terms that we see.
Why the degree is higher?
No, because every time when you are only looking for a factorization mod. So for example, if you look at let's say gk times hk, you end up with some ugly polynomial. But notice that besides x cubed plus x minus y, the rest of them are all divisible by y power 32. Okay, so if I actually did mod whatever y power 32, you just end up with the original polynomial f. So it's a legitimate factorization of f mod y power 32. Okay, but hopefully it's telling you that obviously gk doesn't look like any factor of f, right? I mean, like if I do print of gk, it clearly looks ugly. So it maybe is telling you that, oh, this is how we are going to realize that f was irreducible to begin with. Okay, but yeah, as I mentioned here, this intuition is wrong. And I'm going to give you one example as to why this intuition is wrong. So let's take the third example, which is some polynomial x power 4 minus y squared minus 2y plus 1. Okay. Now let's look at f mod y. What is f mod y going to be? Which is x power 4 plus 1. So if I factor f naught, I get x minus 1 into x plus 1 into x squared plus 1. Okay. So let's take g to be equal to x minus 1. And let's take h to be the other stuff. Okay. Let's run the extended Euclid. You get some a and b. And again, let's lift it to k equal to 5. Again, this is a degree 4 polynomial. So hopefully y power 32 is high enough. Okay. So I get something. And now let's try to print what gk and hk are. And you see that gk and hk are just some random garbage. Okay. And this probably is going to suggest that f of x is irreducible, right? Because like last time we got garbage. But if you try to factor it, you actually get two different factors. So f was not irreducible. But for some reason, once again, when we lifted it, we ended up getting garbage. Okay, so we need to somehow convince ourselves, how are we going to distinguish example 2 and example 3? Okay, hopefully hopefully this makes some sense to you as to why. So clearly something
The other
weird is
makes
happening.
no sense.
Yeah, so we want to somehow make sense of this. Like why did we end up with this? Why is our factor looking like garbage? When in example 1, we had a very nice factor. So let's look at what happened. The actual factors, let's go back here and let's write down the factor of. This is something we don't know, but I'm cheating here and I'm already telling you what the factorization is. So we started off with f mod y and we factored f mod y. So what happened to the factorization of f mod y? So mod y, this became x squared minus 1 into x squared plus 1. Because that's like setting y equal to 0. And this x squared minus 1 term split further as x minus 1 and x plus 1. And we started by lifting this g, which is this x minus 1. Notice x minus 1 is not really corresponding to an original factor of f. It's only part of a factor of f. Like this was the original factor for f. That ended up getting split into two other things. And we chose g to be just one part of it. Okay. And then we ended up lifting. So we end up with some, so in the sense that that's the reason why you're getting garbage, because this is actually, g is not really a proper factor of f.
So this x square minus y minus 1, is that irreducible?
Yeah, this is irreducible. This is irreducible, but unfortunately, when I go mod y, it becomes reducible. So somehow I had an original factorization, but when I went mod y, it decomposed further. And we didn't know better. So we just chose one of the factors and said, let's start with that. And so naturally, when you do this lifting, it seems like you're ending up with garbage. Okay. But it's actually hinting towards something. Okay. So f of x comma y actually had two irreducible factors, x squared minus y minus 1 and x squared plus y plus 1. But it's just that this g star split further as x minus 1 and x plus 1 when you went mod y, and we chose only a part of it. Okay. So in some sense, it's not surprising that it looks messy because it didn't really correspond to a full factor. You chose some partial component of it. Okay, but here is the cool part. Suppose you started off with, instead of x minus 1, this is what we did in the above example. Suppose I worked with x plus 1 and did this entire process. What would I ended up with? Okay, so let's do the same thing. And if you look at gk prime, that also looks ugly. So by that, what I mean is the following. We started off with this polynomial, this g star split as x minus 1 into x plus 1 into x squared plus 1. Okay. X minus 1, when I ended up lifting, I got this nonsense. Okay. X plus 1, if I end up lifting, I get some other nonsense. But this x minus 1's lift and x plus 1's lift put together is a proper factor of f, right? Because that corresponds to this x squared minus 1, which came from a real factor x squared minus y minus 1. Okay, so what I'm going to do is basically look at gk prime times gk. But I get some ugly nonsense. But now look at gk prime times gk mod x power 32. And you end up with y squared minus y plus 1. So all I'm trying to say is that right now, when we started off with g equal to x minus 1 or x plus 1, and we did this lifting process, we got some junk which really looks ugly. So there are terms in there are terms in y that have degree up till y power 31 and whatnot. Okay, but somehow miraculously, if I multiply it with a suitable, I don't know, it's sibling or something, and go mod y power 32, I end up with an actual factor for f. Okay, and I'm just trying to tell you that maybe this is what is distinguishing example 2 from example 3. So you may be able to lift until a certain point, you end up with a gk. Just looking at gk and saying, oh, it looks like garbage is not good enough. What we need to figure out is there something I can multiply to gk which starts making it look reasonable? If you can do that, maybe then it suggests that here is how you find a factor for f. But if you can't multiply gk with anything in order to make it reasonable, that probably is an indication that f is irreducible. So this is the claim that we are going to make. Okay, which is, I want to say f is irreducible if and only if we can find some other gk prime, which is like the sibling of gk that you obtained right now, such that gk times gk prime happens to have the right degree. That is, it looks like a factor of f. That is, its degree in x is strictly smaller than the degree of f, and the degree in y is at most the degree of f. That is, it looks like a proper factor. Okay, this is still a hunch. I mean, the claim is still a question mark. I'm just trying to suggest to you that this maybe is what we need to do, and it turns out that this is true, and that's what we will do in the rest of the class. But I hope that this example is somehow illuminating to exactly tell you, just because the lift looks ugly, we shouldn't stop there. We need to figure out, is there a way to somehow, I don't know, coalesce a bunch of these lifts in order to get a proper factor or not? And hopefully, if f was reducible, we should be able to do this properly. But if f was not reducible, maybe there's just no way to coalesce it into a reasonable factor. Okay, so maybe I'll just take a moment's pause in case people have questions.
Just the last
before looking at the formal proof.
I just got confused.
Okay, so let's just do the following. So here is what I'm suggesting. Okay, so the factorization for f naught was x minus 1, x plus 1, and x squared plus 1. Okay, let's give these three names. Let's call this A. Let's call, okay, A, B, C is a bad example. I don't know. Let's call this P, Q, and R. Okay, let's pretend as if we started off with the original factorization being P and QR. Okay, and we lifted the whole thing. We lifted it to a large enough thing. We ended up with some ugly nonsense. This ugly nonsense is the lift of P. Okay, and now we can do the same ugly nonsense for the lift of Q, which is x plus 1. That will be some other ugly nonsense that happened to be this whatever gk plus gk prime or something. Okay, now I can also do the lift of R. I mean, had I chosen g to be equal to x squared plus 1 and I lifted it, maybe I get some other ugly nonsense. So maybe that is some R or something. Okay, so far so good, I hope. Now what we are somehow saying that it may be the case that the lift of P looks ugly, the lift of Q looks ugly, and the lift of R looks ugly. But the only thing I'm trying to say is that if you take the lift of P times the lift of Q, suddenly that looks very reasonable because that came from a proper factor of f. Okay. So all we want to figure out is that, let's say how would you know whether this is the proper factor of f or not? So you started off with some g, you lifted it, you got some gk. And now you need to know, does gk correspond to a proper factor of f or not? So one way to hope for that is that you can ask, is there some other gk prime that I can multiply to gk so that this product looks reasonable? Okay. And we'll formally prove that the only way the product will be reasonable is f was actually reducible to begin with. If f was reducible, you will realize that there is something you can multiply to gk in order to make it reasonable. And if f was irreducible, there is just no way of doing that. Okay. So let's go back to the notes, and I will now see a formal proof. So I know this is a little confusing because there's clearly something tricky that's going on here. In one case, GK is holding some hidden piece of information which we are trying to extract out of it. In the irreducible case, GK actually is garbage, but we need to somehow be able to distinguish this garbage from, I don't know, this gold somehow. Okay. Okay, good. So let me go back to this thing. Where's my share? Okay, so I hope this thing is back to being visible. Okay, so my iPad screen is still visible now, right?
Yeah.
Okay, so here is what we are basically trying to say. Okay, we ended up, this is what we have computed so far. We have a lift GK, which is high enough. The K is chosen to be large enough. Okay, what I want to do is figure out, is there any GK prime that I can find such that GK times GK prime, if I look at that polynomial mod y par 2 par k, surprisingly looks very, very nice in the sense that its degree is what you expect it to be. Like the degree in terms of x is strictly smaller than the degree of f, like a factor ought to be. And the degree in y is at most the y degree of f, like a factor ought to be. Okay, and the x degree of g prime and the y degree of g prime is again related to the fact that these two must multiply to give g tilde. Okay, and the question is, we want to know, is there such a solution at all? Is there a suitable g tilde and gk prime that satisfy these constraints? Okay, and so there are two things. Firstly, we need to figure out how do you solve for such a g tilde and gk prime. That's one thing. Secondly, even after you manage to solve them, the goal was to eventually pull out a factor of f. So how are you going to pull out a factor of f? So I need to tell you those two parts. Okay. So can someone tell me how you should, how can one go about solving this system, figuring out whether such a g tilde and gk prime exist? So whenever you are in a situation of this sort, just try out, just write down the problem explicitly and it will just jump out at you. So I guess Saurav wanted to say something.
We need to lift it something.
Sorry?
We need to lift it something.
No, at this point you already have. So this is something that we know. So this is given. Okay. What we are trying to find out is these two. So let's just write it down. So
just
what
like
is the left hand side?
Some coefficients.
Right. So this is going to be some g tilde of I comma j.
Can I use some Chinese reminder theorem somehow?
No, it's in fact like, so this, okay, my general advice would be to let's try out first principles. Let's be as dumb as possible. If that doesn't work, we can try out more sophisticated things. But let's just try and write down the what we are supposed to get. So the left hand side is g tilde. I have no idea what these coefficients are supposed to be. But anyway, let's just write down. The left hand side looks like some polynomial expression of this sort. Okay, what's the right hand side? The right hand side is summation. This is GK's coefficients, x bar I, y bar j. I mean, this is something that we know entirely. Okay, times there is this GK primes coefficient, x bar I, y bar j. Okay, mod y bar 2 bar I. Oh, sorry, y bar 2 bar k, right? This is the equation we are trying to solve. So what are the unknowns? The unknowns are actually all of these things and all of these things. Okay. Now notice, now I ask you, what should the constant term here be? Well, the constant term on the left hand side must equal the constant term on the right hand side. And what is that? It's the constant term here times the constant term here. So I'll basically have g tilde 0 comma 0 equals gk 0 0 times gk prime 0 0. What's the degree 1 term going to be, or rather the coefficient of x? The coefficient of x corresponds to I equal to 1, j equal to 0. So that will tell you that g tilde of 1 comma 0 equals, I don't know, whatever you get here on the right hand side. Okay, notice every such equation you write down is a linear equation in these unknowns. Okay, so finding out whether there exists a g tilde and gk prime that satisfies this equation is just solving a system of linear equations. Okay, is this clear? It's just that just write down the expression and it just turns out that all you are doing is solving a linear system. And this we know how to do. I mean, I have a linear system. I mean, we do Gaussian elimination or whatever, and we can solve. So that will tell us, I mean, if there is a non-zero solution to g tilde and gk prime, we will find one out. Okay, are things clear so far?
One thing, the summation is over more than 2 to the power k or less?
Good. So the left hand side, the summation will be like, this I is at most the degree of x and j is at most the degree of y. Whereas this guy, I mean, like, will be corresponding to, I mean, I will go all the way till this and j will go all the way till this.
What do you mean by degree of x?
I mean, so dx just refers to, I mean, this I'm just calling dx and this I'm calling dy. I originally wanted to factor f. So if there was a proper factor, I know its x degree will be strictly smaller than the x degree of f. And the y degree will be at most the degree of f.
And you're also assuming that dy is 2 to the power k is less than dy also, right?
No. In fact, we will be working with 2 power k being much larger than dy. I mean, like Varun said, we'll lift it to a high enough point. I mean, normally you do it in such a sense that you give yourself enough room, like you make it something like d cube or d squared or something like that.
Oh, and due to the monicness, it will be unique somehow.
I mean, the gk is unique, but what is unclear is about g tilde and gk prime. In fact, they will actually not be unique. Once you see the proof of, by the end of the lecture, you will realize that there are actually multiple choices of g tilde and gk prime. I mean, mentally speaking, we know one correct answer for g tilde and gk prime. But since we are just solving a system of linear equations, who knows what we are going to get? We'll end up with some g tilde and gk prime. But the hope is that that has enough information for us to figure out a factor of f. Okay. So maybe just to go over it, let me just write down this claim, because this is what is going to happen. So what we need to do to complete the proof of this, of the bivariate factorization. By the way, so the algorithm is just this. So the do something is solving for g tilde and gk prime. So this is going to be solve for G tilde and GK prime as in, okay, let's give this a name. So let's call this dagger. Okay, and return the GCD of F with G tilde. Okay, and if this is 1, then you return irreducible. So that's going to be the final algorithm. Okay, we are going to try and solve for this G tilde and GK prime. And we had morally convinced ourselves that any G tilde that we find must somehow be a factor of F. And it will turn out you'll have to, it may not be exactly a factor of F, but it will certainly contain a factor of F. So you can take a GCD. So what we want to show is to prove this particular claim, which is that if it so happens that F is a reducible polynomial, then the above whatever this dagger always has a non-zero solution. That is step 1. Okay. Second thing is that no matter what solution you actually end up finding, okay, F will have a non-trivial GCD with that G tilde, provided K is large enough.
Claim to gives the non-uniqueness, right?
Yeah. So the reason that it could be the case that G tilde you might end up choosing a proper factor of G times something. So maybe those are also legitimate solutions to dagger. But the point is, no matter what solution you end up finding, it will actually have a non-trivial GCD with F. And this is the part where we'll use the fact that K was chosen to be large enough. Until this point, K being large enough didn't even feature. Is that okay so far?
Yeah.
Okay, so this is, once we prove this claim, it's clear that the algorithm should work. Because we have lifted it to a large enough K, and we will try to solve for them for a non-trivial G tilde and GK prime. That is something that is non-zero. Obviously 0, 0 satisfies this equation. That's not what we want. We want something that is non-zero. If there is no solution, you return irreducible. If you end up finding a G tilde, then return the GCD of F and G tilde. Okay, and we will be convinced of the correctness of the algorithm if this claim is true. We first want to say that if F was reducible, there better be a solution. And secondly, from any solution, I can extract a factor. Okay, and here is where moniqueness will start playing a major role. Okay, so let's start with the following. So suppose F was reducible, which means that let's say F is equal to F1 blah 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 till some FR. This was the actual factorization for F. Okay, what did we start off by doing? We started off by saying F is equal to G0 times H0 mod Y. Okay, so this basically means that this G0 better divide one of these original factors. So we picked up G0 to be one of the irreducibles, which means G0 must have come from one of the factors. Maybe one of these Fi split further, but nevertheless, like G0 must be related to one of them. Without loss of generality, let's just assume that G0 divides F1. Okay, that is, I'm talking about everything mod Y. Okay, so that is what I'm saying is that say F1 equals G0 times, I'm going to call this G0 prime mod Y. Okay, now here is a monic polynomial and I give you a factorization mod Y, and same all your A, B, etc. will happen. So you can lift this factorization also. You can do Hensel lifting on whatever you have here. Right? So if you were to lift it, what will you end up with? You will end up with some GK. Who knows if it's the same GK at all? Maybe it is some GK hat times GK prime hat mod Y power 2 power K. Okay. Now let's take an equation of the form f1 equals this and multiply both sides with f2 to fr. Okay, so this implies that f equals gk hat times gk prime hat into f2 to fr mod y par 2 par k. But notice we had also done another thing. We had started off with f equal to g naught h naught mod y. And we ended up lifting this to get f equal to gk hk mod y. Okay. And that basically tells us notice that gk was a monic polynomial which was lifted from g naught h naught. But it feels like gk prime is also another monic polynomial that appears to be lifted from, okay, g naught g prime, but had you multiplied this with f2 to fr, you would have gotten the same thing. So this is the place where the uniqueness of monic lifts come in. This tells us that gk prime is the same thing as gk. So by uniqueness, you get that, sorry, gk hat, this is actually equal to gk. Because we seem to have obtained two different monic lifts of the same thing. But we know from Hensel lifting that there are no two different monic lifts. There is only one. So therefore, it better be the case that gk prime is equal to gk. Okay. So therefore, g tilde equal to f1 and whatever gk prime equal to whatever was this gk hat prime is a solution to dagger. Because that basically says that f1 equals gk prime, which now is equal to gk, times some polynomial mod y par 2 par k. And I know that f1 has the right degree. So this particular solution is a legitimate solution to dagger. It satisfies all the properties that you want. So this completes part A, which is that if f were reducible, there is definitely some solution to dagger. Okay, so far so good. Okay, good. Now comes the second part, which is I want to somehow show maybe you found some different solution g tilde. We want to somehow argue that any solution g tilde that you find actually has a non-trivial factor with f. Okay, so we want to show that the GCD of f and g tilde, this is not equal to 1. I mean, that's what we are trying to somehow argue. Okay, so once you see an expression of the form GCD is not, this is what you want to show. You want to show that the GCD between two polynomials is not 1. I mean, hopefully at this point, the resultant is screaming at you. So the most natural thing to do is let's just look at the resultant of f and g tilde and see what it tells us. I mean, we are somehow trying to argue that the resultant of f and g tilde is actually 0, because that's equivalent to saying that the GCD is not 1. Okay, so let's look at the resultant of f and g tilde. So the resultant x of f and g tilde. Okay, notice that exercise that we had earlier, which basically says that the resultant of any two polynomials can be written as a times the first polynomial plus b times the second polynomial. Okay, so this can be written as some a of x comma y times f plus b of x comma y times g tilde. Okay, and the only information we have about g tilde is something about, you know, g tilde being equal to gk times gk prime mod y par 2 par k. This is all we know about g tilde. So let's take this equation and go modulo y par 2 par k and see what we get. Okay, when we go mod y par 2 par k, what do I know about f? we kept lifting. So I know F is equal to GK times HK. Okay, so this you end up getting, I'm going to remove this X comma Y business. So this is equal to GK times HK plus B times G tilde was basically equal to GK times GK prime. So far so good. So this is basically equal to GK into AHK plus B times GK prime. Okay. Good. Now I want to look at this equation and basically say this equation is absurd. Now, why is that? What can I say about the left-hand side? What sort of a thing is the left-hand side?
It's a polynomial in X, right?
No, it's a
Y.
polynomial in Y alone.
In Y alone.
Right. So this is something that is a polynomial in Y alone. Okay. What do I know about GK?
It's in X and Y both.
It's in X and Y, but more importantly, it's monic.
Monic.
Right. So this guy is monic.
I see. You're saying there will be some terms X will be left alone with the
yeah. So basically, how can a monic polynomial times something suddenly become a polynomial that depends on only the Y variables? Okay. I mean, it's okay. If this was not monic, maybe it had a Y in the beginning. Then you could have argued that no, I multiplied by Y power 2 power K minus 1, and suddenly it became that term vanished. You could have said something like that, but we are assuming that GK was monic, which means there was a term that was purely in terms of X's. And how could that get cancelled off on the right hand side? The only way that can happen is if this was actually equal to 0 mod Y power 2 power K. I mean, the only polynomial that can be a multiple of a monic polynomial and still be a polynomial in the Y variables alone is the zero polynomial. Okay. So we are almost done. What we now know is that whatever was this resultant is a polynomial that is divisible by Y power 2 power K. Okay. What I want to show is that this is actually zero without the mod. That's what I would like to show. Okay. So far, we have not used the fact that K is large enough. Until this point, everything that we have said just works for any K. Okay. But again, now let's say the following. So this basically means that the resultant X of F and G tilde is divisible by Y power 2 power K. Now, can you set K large enough such that this basically means that it better be the case that the resultant is zero?
It is for all K it holds. That's also.
Yeah, right. So what sort of K should you choose so that you are guaranteed that this automatically means that this is zero?
That is degree.
That's right. So what is the degree of this guy?
At most 2D.
2D squared or 2D squared. So I just need to make sure that this 2 power K is bigger than 2D squared. That's it. Once 2 power K is bigger than 2D squared, saying that the resultant is divisible by this automatically implies that the polynomial better be zero to begin with. Otherwise, how can a Y power 2 power K divide something whose degree is smaller than that? Okay. So this implies that resultant X of F and G tilde, this is equal to 0 if 2 power K is bigger than 2D squared. So in the above algorithm, when we were saying choose K large enough, what we actually are doing is like this K such that this 2 power K is bigger than 2D squared. And yeah, and that's the bivariate factorization algorithm. It's a pretty cool algorithm. I mean, in the sense that it's very easy to have come till this point, looked at GK, and then basically said, oh, damn, I mean, like this is not giving any information. Okay. And somehow the resultant is exactly, I mean, like the perfect thing that you needed in order to figure out, is this GK useful or not? And you can figure out if this GK is useful or not by just solving the system dagger. If you manage to solve the system dagger, you know for a fact GK is useful, and this G tilde already has a factor of f that you're looking for. Okay, and that's it. This is the whatever the Fonsor Gathen Gathen bivariate factorization algorithm. Okay, so maybe I'll take just a few more minutes to tell you a little bit about these some assumptions that we made. One of which was that I would like to assume that f of x comma 0 is square free. So that was one thing. And secondly, we also made this assumption that f is monic. I mean, ideally, we would like to get away with all of these. Like we shouldn't have to make these assumptions. Ideally, we would want a bivariate factorization algorithm that works for all bivariates. Okay, so what do we know? So we know that we have a monic f of x comma y that was square free to begin with. Square freeness we can arrange for by taking GCD with its derivative. Okay, but when will f of x comma 0 not be square free? Okay, and this is precisely when the resultant of f and f tilde with respect to x, but when I substitute y equal to 0, this becomes 0. Okay, fine. And the only thing to keep in mind is that, if the size of our field was large enough, like 2D squared or something, there is some alpha such that this resultant with respect to x of f and sorry, not why did I write f tilde? What I meant was the partial derivative. I mean, whichever partial derivative you end up taking. Okay, this at alpha continues to remain non-zero. Just because of the fact that I know this is a non-zero polynomial. Had I not substituted alpha, that polynomial has degree at most 2D squared. So which means there can only be at most 2D squared many points on which it becomes 0. So if my field is large enough, one of these points is going to be non-zero. And at this point, what you do is you end up factorizing f tilde of x comma y, which is defined to be f of x comma y plus alpha. So run the entire algorithm for this thing, basically because this condition is satisfied as long as the resultant does not vanish on 0. And I'm just shifting that 0 to the alpha. Okay, it's one of these standard tricks that is followed in order to make sure that you can deal with the situation when the resultant does not vanish at 0. So obviously, if you know the factors of f tilde, you also know the factors of f, because I just undo the substitution of y to y plus alpha. Okay, this is how you justify that you can assume that f is square free. Okay, and the annoying thing is that, if the size of f is too small, there is some, I won't get into this, do some extension jugaad. Okay, so there is some extra bells and whistles you need to throw in to pretend as if you are working on a slightly larger field. Okay, I'm not going into the details of this. It's unnecessary details which complicate the situation. Okay, so this is basically why you can sort of assume without loss of generality. By that, without loss of generality, what I mean is, if it so happens that f of x comma 0 is square free, then maybe f of x comma 7 is not, if f of x comma 0 is not square free, maybe f of x comma 7 is square free, so I can deal with some version of that. Okay, so that is trick 1. Now, trick 2 is similar to what Saurav had mentioned earlier. So suppose f was not monic. How do I somehow make sure that f was? I deal with a polynomial that is monic. I only know to factorize monic polynomials. And can I massage this f into some other monic polynomial such that factorizing that gives me the factors of this? Okay, and here also is a nice trick. You work with the following polynomial, f of x comma y, which is, you do the following. You look at f of sorry, f of x by fd, comma y.
Sorry?
Okay.
Oh,
Okay. And because there are these stupid divisions that are involved, now I'll multiply this with fd power, I think, d minus 1. And if you notice this should basically become x power d plus fd minus 1 times x power d minus 1 plus fd minus 2 times fd times x power d minus 2, etc., etc. Because this will contribute so this guy will contribute an x by fd the whole power d, and I'm multiplying by fd power d minus 1, so that cancels off, so I get x power d. And every other term, I might get a denominator of something that looks like fd power something. But fortunately, the thing outside is large enough such that it cancels off those denominators. So I now end up with a new polynomial, which now magically is a monic polynomial. Okay, and I will let you figure out that factors of f.
you assume that if all the lesser coefficient will divisible by fd.
No, I didn't. I'm just saying, so this is the original polynomial.
Yes.
Now, when I make the substitution x, I make the substitution of x by fd. Let's
Yes.
look at all the other terms. What do I end up getting? I will end up with something that has fd power I in the denominator, where I is at most d minus 1 for all the lower order terms.
Yes.
Right? And since I'm multiplying by fd power d minus 1 on the outside, I can cancel the denominator off.
Okay. Got it.
Okay, so a simple exercise is that the factors of f can be obtained from factors of f tilde. So if this is the polynomial that you're asked to factorize, you instead factorize f tilde, and from that somehow figure out what the factors of the original polynomial f was. Okay, and it's not hard to see how the factors are related. It's very easy to figure out what's happening. Okay, so let me just conclude by saying this is the final Gathen-Kaltofen algorithm, which is we did it for bivariate, but notice that the only thing about bivariates we used is that we know how to do GCD in the univariate setting, and we know how to do factorization in the univariate setting, because we just piggybacked on top of what we knew already. And now that you know how to do bivariate factorization, you can now do trivariate factorization exactly the same way. Okay, and this process will eventually, if you unravel it, you end up with a running time of poly in n power k and log q, where if you're dealing with k-variate factorization. And this is also called polynomial time in the dense representation, because if someone were to give you a k-variate polynomial, they need to give you n power k coefficients. So at least, I mean, it seems to be polynomial time in the input length, assuming that I tell you all the coefficients. So such a thing is called a dense representation, and it gives the polynomial time, a polynomial time randomized algorithm in the dense representation. Okay, I've already gone well over time. So in the next couple of lectures, we will build on what we have. I mean, this in my sense is the final peak of part 2, which is to see factorization over the rationals or integers, because I presume most of the time these are the polynomials we're interested in. I mean, like, you know, we probably don't care, you don't care as much about finite fields and so on. We are mostly interested in factorizing integer or rational polynomials. But bivariate factorization will be very, very useful for factorizing over Zx, surprisingly, even though we are dealing with one variable here. Somehow it has a very close connection with bivariate polynomials over finite fields. And that is what we will do in the next couple of lectures. Okay, so let me stop here. I'll just maybe take questions if there are any. I'm sorry I went over time. I mean, we started late because of that stupid fire alarm thingy. Yeah. So are there any questions? Okay, cool. So if there are no further questions, then let's meet on Tuesday. Yeah. Okay, see you all.